Hi everyone. In the previous class, we discussed the critical thickness of insulation for a cylinder and understood how important is the selection of proper thickness for insulation. In this tutorial, we'll work out an application problem involving critical thickness of insulation. Let us work out an example.
A 10 mm diameter cable is to be laid in an atmosphere of 20 degrees centigrade with H0 is equal to 8.5 watts per meter square degree centigrade. The surface temperature of the cable is likely to be 65 degrees centigrade. Discuss the percentage increase in heat transfer for the same cable surface temperature if the cable is insulated for maximum heat dissipation with rubber having thermal conductivity of 0.15 watts per meter degree centigrade. So you have a 10 mm diameter, very small diameter cable, and it has to be laid in an atmosphere of 20 degrees centigrade. So ambient temperature is given, outside heat transfer coefficient is given, the surface temperature of the cable is given 65 degrees centigrade. So we have to find out the percentage increase in heat transfer when the cable is insulated with rubber having thermal conductivity 0.15 watts per meter or degree centigrade for maximum heat dissipation. The intention of insulation is to increase the heat transfer and maximize the heat dissipation, and the insulation material used is a rubber with a thermal conductivity of 0.15 watts per meter degree centigrade. So first you need to find out the critical radius of insulation and critical thickness of insulation, and you have to insulate by providing that critical thickness of insulation, which will increase the heat transfer, and keeping the same cable surface temperature 65 degrees centigrade. You have to calculate what is the heat transfer from this insulated cable, and then you can find out the percentage increase in heat transfer. So these are the data given. Cable surface temperature is T1 and 65 degrees centigrade, ambient temperature 20 degrees centigrade, thermal conductivity is given, that is thermal conductivity of the insulation material, it's not pipe material. The insulation what you are providing will have a thermal conductivity 0.15 watts per meter degree centigrade. Outside heat transfer coefficient is given. So R1 is, for this diameter is given, so R1 is 10 by 2, diameter by 2 is 5 mm, 0.005 meter. Now you can find out the heat transfer from the bare cable. When it is bare, before insulation, what was the heat transfer from the cable surface? Cable surface temperature is 65, ambient is 20, and you know that convection resistance is 1 by AH0. So you can use this equation, temperature difference divided by convection resistance. So area you can substitute, area, outside area, convection is happening from the outside surface, convection area is perimeter 2 pi R1 into length, that will give the area into H0, that is, so you can write 65 minus 20, T1 is 65, ambient temperature is 20, divided by R1 is 0.005, for 1 meter length you are calculating, okay. So a length is taken as 1 meter and H0 is 8.5. You will get the heat transfer from the bare wire as 12.017 watts. Now let us calculate the critical radius of insulation. And the quality of the thermal conductivity of insulation material is given. It is 0.15 watts per meter degree centigrade, and outside heat transfer coefficient is given 8.5 watts per meter square degree centigrade. So you will get the critical radius as 0.01765. That means this is so much meter, so that means 17.65 millimeter. 17.65 millimeter. The radius is only 5 mm. Radius of the bare wire is 5 mm. Now critical radius you are getting 17.65. So since the critical radius is more than R1, this addition of insulation will increase the heat transfer. Suppose you are getting less than 5 mm, insulation using rubber will not increase the heat transfer, it will always decrease the heat transfer. So since the critical radius is more than the outer radius of this wire, addition of insulation will increase the heat transfer. So this is the radius of the insulation to be provided for maximizing the heat transfer. Now we will find out the heat transfer from the insulated wire. So the temperature we want to maintain the same. So when you provide the critical thickness of insulation, more amount of heat starts flowing, the temperature will decrease. So the temperature decreases, you can allow more amount of current to flow through the cable so that the temperature can be maintained at 65. So this insulated cable can permit more amount of current to flow through this. So we are finding out the heat dissipation when the cable surface is at 65 degrees centigrade. When it is 65, what is the heat dissipation? So we'll find out by keeping that T1 as 65 and ambient as 20 degrees centigrade. So the equation is for T1 minus Ta divided by conduction resistance plus convection resistance. But outer radius is critical radius. So here again area is 2 pi RCL. Now we'll substitute for T1. T1 is 65, ambient is 20 and the thermal conductivity is 0.15. Length for 1 meter length. The RC we got the critical radius as 0.11765 meter. And R1 is also known, outer radius of this wire 0.005, and again substitute RC and H0, will get the heat loss from the insulated wire as 18.757 watts. Now the heat loss is more, heat dissipation is more. Why more amount of heat is dissipated? Because the cable, we are keeping the same cable surface temperature. So same current flows, same amount of heat will be generated. And if you are providing insulation for the same current flow, temperature will decrease. The temperature of the cable surface will decrease. Here, keeping the same cable surface temperature, what is the heat dissipation? So you are keeping that 65. By providing the insulation, you will be able to increase the amount of current flowing in this cable, because this heat dissipation rate has increased for the same cable surface temperature, so the cable can transmit more amount of current through it and keeping the same cable surface temperature. So by adding this critical radius of insulation or critical thickness of insulation, the wire will be able to carry more current, keeping the cable surface temperature 65 degrees centigrade. So we got heat flow from the bare wire and heat flow from the insulated wire. Now we have to calculate the percentage increase in heat transfer. So percentage increase in heat transfer is Qi minus Qb divided by Qb into 100. So Qi you got from insulated wire, heat transfer is 18.757 and from bare wire it is 12.017 divided by 12.017 into 100. So you get the percentage increase in heat transfer as 56.087. So keeping the same cable surface temperature, the amount of heat transfer has increased by 56.087 percentage. So this is the increase in percentage of heat transfer by providing for critical thickness of insulation for the cable. Thanks for watching. Keep watching this channel for more such videos.